And to understand how gravity works and kind of how the stars and the universe works, we need to understand Newton's second law. Isaac Newton was this famous scientist that we've talked about earlier, who kind of figured out what holds everything together in the astronomical sense. And so today what we want to do is we want to look at Newton's second law. And as we look at his second law, we're going to kind of learn how the planets work. And well, we won't necessarily learn that today, but we will be getting some information that will help us understand that in subsequent discussions. So here we are, podcast 2.2, Newton's second law of motion. Now there's a lot of text here, so you probably want to copy this down, pause the video, but let's kind of talk about that. There's a couple of important things. We need to understand the concept of acceleration. Now we have talked about that previously, but let's kind of talk ourselves through that. Acceleration is an object's increasing or decreasing speed along a straight line. That is accelerating. So if I have a vehicle that's going very, very fast, actually let's kind of illustrate this right here with a video clip. Okay, today what we want to talk about is acceleration. How does something accelerate? Now there's actually two ways to accelerate. The first way that we accelerate an object is that we change its velocity. So let's talk about it with this ball on the table. Now the ball, of course, is at rest right now, but if it's moving at if it's moving at one speed, it's moving at the same speed. That's not accelerating. But if I change the velocity real fast, then that is changing the velocity. Now that's actually called acceleration. You can also decelerate, which is still acceleration in the negative direction. If it's going real fast and then it starts going slow, that's deceleration. But there's also another way, that's kind of cool, isn't it? There's another way that an object can accelerate. It actually can be moving in a circle, and that's also accelerating because what it's doing is it's changing its direction. So acceleration has to do with changing direction or speed. Okay, so let's illustrate the acceleration by watching another quick little video clip. Now the second way that you can accelerate an object is actually by changing its direction, not just its speed. And so if the ball is moving in a circle, it is actually constantly accelerating. Actually, maybe we'll do it this way. It's constantly accelerating because it's changing its direction. I don't know if you've ever been in a car, and when you're you probably have been. If you're in a car and you go around a corner real fast and your body goes over to the side, that's because your body is still moving in one direction because you're still accelerating in one direction as it goes around a corner. So that's another way to accelerate an object. That's pretty cool too. All right, now let's talk about what causes something to accelerate, to increase its speed or decrease its speed or to change its direction. Acceleration is produced by a force. And it's interesting that when you do experiments, if you apply this thing called a force, we'll talk about that in a second, that they are proportional. That's a big fancy scientific or mathematical term, proportional. That means, by the way, what does proportional mean? So let's kind of talk ourselves through that. Proportional means if you double one thing, so double the force, okay, then they're proportional. Then the acceleration is doubled. If you half the force, the acceleration is halved. If you triple the acceleration, it is tripled. That's said to be proportional mathematically. They're factors of each other. Okay? That leads us to understanding how gravity is an acceleration. Or actually, there's an acceleration due to gravity. So let's watch a short video clip that explains that. Alright, now what I want to talk today about is gravity. What is gravity? Now gravity is kind of a weird thing to understand. Gravity is the attraction of one object for the next. So if I have a book and a piece of paper, then technically they're attracted to each other. But if I let go of them, they don't really attract to each other. They just like fall to the earth, right? Now what's going on with that? Well, that's actually because the earth is a bigger object. It's a more massive object. And since it's more massive, the paper and the book are much, much more attracted to the earth than they are to each other. But if I were to have these two out in space, they would come together. Now, because we have the earth, we're standing here on the earth in our high school, we can drop them. And an interesting thing about gravity is that the acceleration of gravity is the same regardless of the mass, whether you have a heavy book or a light piece of paper. So, of course, they're going to land at the same time. They didn't. I wonder why. Oh, you know, wonder? What if I were to have a couple of books? Actually, let me grab another book here. What if I had 2 books versus 1 book? This weighs twice as much as 1 book, your astronomy book. What's going to happen here? Now, if I were to drop these, they landed exactly at the same time. So twice the mass, you'd think it fell twice the speed. It didn't. You see, it doesn't matter the mass. The reason that the paper here does not fall at the same speed is because it has a lot more air resistance. And these can overcome the air resistance. To illustrate that, what if I were to take the books, the 2 books in the 1 book, and I'll put the piece of paper on top. And when I put the piece of paper on top and I drop them exactly at the same time, they should land at the same time. And they do. That's what gravity is. Wow, that was pretty cool. There's a thing called the acceleration of gravity, and we can understand that. And it's constant all over a particular planet. And for our planet Earth, that number happens to be, the acceleration of gravity, or A, is 9.8 meters per second squared. All right? That would be very important to write down. All right. Now let's kind of talk about what this all works out to. Now, obviously something that has more mass is going to have a different kind of a issue. So let's take a look at mass. Mass is the amount of matter an object contains. That doesn't sound right. Actually, that's just right. I just was confused. So the amount of matter in an object is the mass. All right. So if we have a spaceman guy here, I don't know which one he is, but what you've got here, he has a particular mass. Now, the interesting thing about mass, I'll be able to understand, his mass doesn't change even if he's on the moon, as this guy is, because that has to do with the acceleration of gravity. Okay. Technically, mass is a measure in objects' inertia. And we haven't talked too much about inertia, but let's go ahead and make a note of that. Okay? Which we're now going to see the same things twice. I don't know. Oh, yeah, no, this is it. Okay, mass is also generally measured in a unit called a kilogram. The abbreviation for a kilogram is a kg. All right, so that's the unit that we use for kilograms. But do not confuse it with weight, which is a force related to gravity. Weight may change from place to place, but mass does not. You see, when you're on the moon, for example, you weigh 1/8. It might be 1/6. I can't exactly remember. You weigh 1/8 of that of you do on the Earth. That's because the moon is less massive, and we're going to talk about that when we talk about gravity in our next podcast. But your mass would remain the same. Mass is constant. Doesn't change for a particular object. I guess if you were to lose weight, you would have less mass. But in that sense. But if you were just to stand here on the Earth and then go stand on the moon, your mass would remain the same, but your weight would be different. There is a difference. All right, the big fancy equation that you should probably already have copied down is F equals ma, where F stands for the force. Actually, let's put that off for a second. Let's make sure we understand what each of these symbols are. F is the force. May the force be with you. No, that's something different. Yes, I know you were thinking that was funny. Okay, the force is measured in a funny unit called a Newton. Okay. Isaac Newton. We named it after him. You'll see. Mass, him, is mass. And mass is measured in kilograms. And acceleration, okay, acceleration, A is acceleration. I shouldn't say that. And that's going to be meters per second squared. So now if you think about it, if you have an m times an a, then that will be a kilogram times a meter over a second squared. That's actually the unit for a Newton. That's called a Newton, or capital N. The Newton. All right. So equivalently, the amount of acceleration, a, that an object undergoes is proportional. That means you multiply, not that double thing or triple thing, to the force applied, F, and inversely proportional to the mass of an object. You know, this is not that important that you write that down. I think I'm just going to have you say, cool, Mr. Bergmann said that, don't write it down. Yeah. It's more important that you get this part, sort of the mathematical piece, okay? Because we're going to do a couple of mathy problems. We like math. Math is good. This equation applies for any force, by the way, whether it was gravitational or otherwise. This is important to write down. We're going to be primarily talking about the acceleration of gravity, but I can accelerate a car on the road or whatever. It applies. This law is not just related to stars and planets, but it's related to just anything. So it's a kind of a universal law there. Okay.